Hi everyone, welcome back to the channel. So today we're going to be working through some physics concepts. We're going to do work and energy. So let's get started. So work, we need a definition of what that means, right? Because work in our daily lives is just work, but in physics it's very specific. So work in physics has to do with a force being applied on an object and the object moves some distance, okay? So we're going to start with work done by a constant force, and a constant force is basically a force that doesn't change over the duration. So if you push an object, you only push it with a certain amount of force. You don't continuously push harder and harder every meter that it goes. So if you're confused, we're going to go over it in just a second, okay? And the examples will make a lot more sense. So let's go through the examples. So let's say you have this object right here and you push it with a force of 10 newtons this way, right? But you have to keep in mind there's friction between the object and the plane. So the force of friction is 20 newtons. So you have 10 newtons going this way and 20 newtons going that way. So what's going to happen? You won't be able to move the object, right? So if it doesn't move, it wasn't displaced any distance. So your work is equal to just 0 because no work has been done. Okay, that's where you have an example of no work being done. So what does work being done look like? Okay, so if we want to see what work done looks like, we can do it with either, let's start with complete flat plane, right? They're just a flat plane. So you have some object here on a flat plane, and you have a force of 30 newtons going this way and 20 newtons of friction. So what happens is it starts to move, right? So it gets displaced. Okay, so we're going to ignore this side right here, okay? And let's just focus on this. So the equation for work is, like we said, work is equal to a force times the displacement of that object, right? So let's take a look. Force, we're used to forces. It's measured in newtons, and newtons has a unit of kilograms times meter per second squared. Okay, it'll make more sense why I'm saying this in just a second. We also have our displacement, which is in meters, like we're used to. And then we have work, which is measured in joules, which is something we may be unfamiliar with because we haven't gone over it before. So joules is equal to kilograms times meters squared over seconds squared. So if we go back to newtons, kilograms times meters divided by seconds squared times meters gives us the unit of joules. Okay, so this is the equation for work on a flat plane. There is no angulation at all. So this is helpful if you're on a flat plane, but what if instead of pushing the box, you want to pull it, right? You're standing on a ledge and you're trying to pull it this way, right? It's still on the plane. So let's take a look at what it looks like when work is being done at an angle theta. So we have our applied force of 30 newtons going this way at an angle. So what we have to do is first split it up into its component parts, as we see here. This is so that we understand what's actually moving the box in the direction of motion, perpendicular to the plane. So that's a lot of big terms. What I'm saying is, what's going to move the box forward or backward in terms of so your box is here and your plane is here. So between the box and the plane, what's going to move this box this way or this way on the plane, right? Not up and down, this way and this way, right? So because that's what's happening. So let me show you with the free body diagram over here in the corner. So you have this object, it has a normal force and it has its mass times gravity. So its weight and the normal force. So since this is in equilibrium, it's not going through the plane and it's not flying off the plane, right? Then this y direction isn't important in this case, right? There's no work being done because it's not displaced in the y direction. We can see that here. If you set it up, F net is equal to ma. It's just normal force minus mg, so they're equal to each other, right? And so the object, again, doesn't fly up and it doesn't fall through the surface. So what we want to focus on is, where is work being done, right? Because I've made the claim that there is work being done, so let's figure it out. If we look at the x direction, right, we see that we have a net force, and so we need to figure out how I got to here, right? So let's go back to the free body diagram. Remember, there's a force of friction going this way, and there's some force pushing it this way, right? That force is at an angle, so it's like that, right? So you get a little triangle. So what you want to do is split the vector of the applied force right here into its component parts, x and y, right? And so if you look specifically at the x direction, remember how we said there's nothing happening in the y, so we can just ignore that, right? So in the x direction, what's happening is there's some force being applied to the box going this way, right? That way, to the right. And then there's some friction force. So object wants to go like this, friction's going like that. So who's gonna win? Let's take a look. So let's break this up into a triangle so that we can use our trigonometry functions. So what we see here is x is over here. So what we can do is use cosine of theta, right? So what we get is the force applied times cosine theta is equal to the x component of the force applied, right? So what we see from there is now we can go back and look at our net forces. So we see that F net is equal to F applied cosine theta minus the force of friction. Because remember, the motion is positive this way and it's negative this way. So we have to figure out the overall forces in the x direction. So what we get is this function right here, right? And so if we go from there, we need to figure out, well, how does the net force relate to the work being done, right? So let's go here. Let's go back. Remember, work is a force applied on an object and the object moves some distance from its starting point. So in this case, now we have our force. We're going to focus specifically on the applied force, right? So if we look at the applied force, it's only the x component of it is actually doing anything, right? So the F applied of cosine theta goes right here. You see that? So the work of the applied force is equal to the force times cosine theta times the distance, right? And remember what we said over here, work is equal to force times distance. Well, because of that angle, the force applied times cosine theta times the distance, not just the distance. Okay, and if you want to get technical here, it would technically be, it's always going to be cosine because it's perpendicular to the plane. So you see how those two are like that? So the angle has to be from here up. And so you're always looking at it in terms of the plane. So again, it's almost always, it's going to be the x direction in this case, right? So it's always going to be cosine, right? Okay. So now that we have a better understanding of work being done and work being done at an angle, let's keep in mind one more thing. Let's go through our side note. So keep in mind, you can have work overall, or you can have work of a single force. So I wrote that here for you. This is the work of the applied force. Again, to be very particular, it's the work being done on the object by the applied force. And then you have your net work, is equal to F net d cosine theta. So it's the same equation, but instead of just one force, we're focused on the overall forces creating work, right? So let's move on to the next part. So there's various different forms of work, right? And if you have multiple forces on one object, you can add to find the net work, which we just talked about. But let's take one step back and look at the different forms of work. So this is an object with a force being applied to it, right? It's at a flat plane, like we said. So in reality, it's actually the force times the distance, right? But it's times cosine of theta. But theta is 0, right? And cosine of 0 is just 1. So when we go to write that work equation, we just do work is equal to force times distance, right? And remember, there's no angle here. It's just 0. So let's go to a different example where there is a slight positive. So now what we see is what we had before, which is there is some angle now. It remains cosine because it's perpendicular to this plane. So how is this object moving in comparison to the plane that it's on? And that would be always cosine, right? So that's where we get the same equation, but we'd have to substitute in theta, right? Whatever angle theta is from the perpendicular, from the plane, okay? So this would be slightly positive work, okay? This would be the maximum amount of positive work that you can have because the work is just purely it's purely moving the object this way. There's no resistance, okay? What you have over here is slightly positive. There's some resistance. It's not necessarily 100% of the force being applied this way. There's a little bit of the force in the y direction as well, which is right here. So now you have a case of no work being done at all. And what that looks like is a 90-degree angle. So if you have a force that's just going directly up, what happens is in terms of like this plane, like we keep talking about, always in terms of the plane, this object is not moving with the plane. It's not going this way or this way. It's going that way, right? So there's no work being done on the object in this case because in the x direction, in terms of the plane, there's no work being done. It's not displaced that way. Okay, and then let's go to the maximum amount of negative work that you can have. So think about it like this. If you have this object right here and you have some force going the opposite way of the plane is right here and the plane you want to go this way, right? That's the positive direction. The force is being applied the opposite way. It's moving the other way. And so what that gives us is the maximum negative work, which means that work is happening, but it's negative because it's going against the plane rather than with the plane. And then what you have over here is a different form of slightly negative, right? Remember, there's an x and y component of this vector. And so what you see is that, again, it's moving this way instead of this way. So it's going in the opposite direction of the motion of the plane. And so it has a y component and an x component. So it's not purely x being moved to that side. So it'll be slightly negative work. So let's work through some examples. So we'll start with this example, right? So you can read through it as well if you need to, but I'm gonna read it out loud. So student holds her psychology textbook, which has a mass of 1.5 kilograms, right? That's important. Out of a second-story window until her arm is tired, then she releases it. So question A is asking, how much work is done on the book by the student simply holding it out the window? So let's start there. Let's make a drawing, or they have a drawing for us. So remember the mass is 1.5 kilograms, right? And she's just holding it. So in that sense, nothing's happening to it, right? I didn't draw a free body diagram, but I thought this would be a little bit easier. Basically, you have your textbook and it's not moving, right? It's just sitting there. So if it's just sitting there, even though there is a force being applied by gravity because it's heavy, it has some weight, it's an equilibrium. mg is equal to Fn. These two are the same. So nothing's happening. So if it's not displaced at all, then your work is 0. Okay. Now, part B of the question is how much work will have been done by the force of gravity during the time in which the book falls 3 meters. So now something is changing. The book is falling 3 meters, right? So let's start with our mg, right? There is no force going up. It's just falling straight down, right? And so what we see is there's a 3 meter displacement. So if we go back to what work is, we said that work, let me write it out for you. Work is equal to force times distance, right? Work is equal to force times distance. So in this case, the only force acting upon this object is our mg, which is our weight, times the distance. So all you do is plug it in, just plug in your numbers, right? And what you get is 44.1 joules. So I wrote it right here for you. Remember, work is equal to force times distance. And I wrote out joules is equal to kilogram meter squared over second squared. And newtons is equal to kilogram meters per second. The reason I wrote out the units is because this could have been in centimeters, for example, and we'll see cases like that later. So always be careful. This could have been in grams, right? So always be careful with your units, otherwise you will get the wrong answer by an order of magnitude, right? Either 10 or 100, depending on which incorrect unit you used. So keep that in mind just for future reference. Let's go to example 2. So if a person pushes on a lawnmower with a constant force of 90 newtons at an angle 40 degrees to the horizontal, how much work does she do in pushing it a horizontal distance of 7.5 meters? So let's break this down. We have our applied force, which is a push, and I wrote it right here, a force applied of 90 newtons, right? Keep that in mind. It's a constant force. It doesn't change. At an angle 40 degrees to the horizontal, right? To the horizontal, it's just talking about the plane, right? So if our plane is right here, it's horizontal to that plane, right? So it's the same thing that we had earlier. It's the same as these, right? But in this case, the plane is just above, not below. But it's the same exact thing. So let's take a look at it. So let's write out what we have, what our information is. We have our applied force, we have our distance of 7.5 meters, and we have our theta, right? So let's go back. Remember that work is equal to F force times distance times cosine theta, right? We ignore it when it's a flat plane, but we know that there's an angle here. So just plug in your numbers, right? So what you need is your applied force times your distance times cosine of the angle, and you get your answer of work is equal to 517.1 joules. Okay. So we're gonna stop after this example, but this is the most difficult one in our lecture today. So let's start with this one. I'm gonna read it and then we're gonna break it down step by step, okay? So example 3. So a 0.75 kilogram block is sliding with a uniform velocity down a 20-degree inclined plane. Question A is asking how much work is done by the force of friction on the block as it slides down the total length of the plane. Okay, we're gonna stop right there. Let's work on A. So what do we know right now? This is what it looks like. Okay, so we want to figure out, okay, which way is positive, which way is negative, right? I prefer, you can do it the opposite way if you want to, but based on what the problem is saying, it's sliding down the ramp. And so the motion is this way. So to make it easier, just keep this as positive, right? And then going straight down, you can keep as positive because again, it's sliding down the ramp, not sliding up the ramp, right? So this will just make your life easier. And so let's start with the free body diagram to see what this actually looks like, right? What forces are acting upon this block. So we have our mg, which is its weight, right? And in accordance with that, we also have our normal force, because again, it's just sliding down the block. It's not flying off the block, and it's not flying off the ramp, and it's not going into the ramp, right? So keep that in mind. So now what we see is, once we break it down, we have our normal force in the y direction, and we have our force of friction in the x direction, right? So let me write that down, y direction, x direction. So what we need to do is, so in case you're unfamiliar with a free body diagram that's rotated, what you have is a block, right? And this, just pretend that the block is right here and mg is just going straight down, right? So what's happening is, to make your life easier, you just want to rotate it, right? So that it fits with the block. And so what that looks like is, instead of, if you go like that, you'll see where this came from, right? That way it makes your life a lot easier, and you're not splitting everything into its component parts. You're treating the normal force, which is always perpendicular to the surface, and yeah, you're keeping this perpendicular to the surface. And then what you want to do there is also the friction, just keep it perpendicular to the surface, right? That way you can call your normal force your y, and you can call your friction force your x. That makes it a lot easier. And then the reason for theta being over here is because mg wanted to be straight down, right? But we rotated everything this way, right? So if you start over here, you start with it like this. And so what happens is, you shift everything away, right? And so what happens is, mg is always going to be straight down, right, from the block. So it's always going to be straight down. So what you do when you rotate the axes is, you take something that was straight and it remains in its place, right? And then everything else around it starts to tilt. And so you get a theta on the right side of it, right? And it would be, if it was the other way, you could do it the other, well, in this case, it's not the other way, but in this case, again, your mg is going straight down. Everything was like this, and so you moved everything this way. Mg doesn't move. So what happens is, now you have some angle in between, and that's your 20 degrees. So we break this down into its component parts, and we get this triangle right here. And as you can see, if you use your, we just went over this in the last problem, so use your trig functions to find the x component, right? Because again, it's an equilibrium in terms of, it's not flying off the page, and it's not going into the ramp. So what we want to do is figure out the x direction of it. We're going to ignore the y in this case, because we are claiming that it's in equilibrium, okay? So if we focus only on the x aspect, we'll see that F nat is equal to mgx minus the force of friction. So basically we are saying that the x component of the so we could just do this. We're calling this mgx. Let me write that better. We're saying that's mgx is what's opposing, it's what's causing the block to move down the ramp, and what's opposing the motion is the friction. So when we solve for that, and we call it mg sine 20, so what we get is, it's not accelerating. We were told it's in constant velocity. Remember, uniform velocity means no acceleration is occurring. So what we can do is we can just completely remove ma, becomes 0. So what we get is our force of friction in the end. When we solve for it, we get our force of friction is equal to 2.51 newtons. Great. So now what do we do with this, right? Let's go back to what the problem was asking. How much work is done by the force of friction on the block as it slides the total length of the plane, right? What's our work equation? Remember, work is equal to force times distance cosine theta, okay? So what we need to do is figure out, one, what is the distance? Our distance is right here. It says the entire block is 1.2 meters. That's where we get this, right? And then our force is 2.51 newtons, which we got from here. So now everything's kind of coming together. So now you may be confused as to why it's still cosine theta, right? And so what some people do is they'll take cosine theta and say, oh, theta is 20 degrees, right? Theta in this case is not 20 degrees. Why is it not 20 degrees? Remember, it's in terms of the motion and the plane. So I drew it out right over here. So what you see is the block is right here. Its motion is going this way and the force of friction is going that way, right? And so what you see is between the motion where the work is being done and the force of friction, which is kind of holding it back, you can just ignore the friction. Think about the motion in comparison to the plane. So what I did was take a look over here. This is the plane, and this is where motion is going, right? And then add friction back into the equation. Friction is going opposite of that, right? So cosine theta would be the distance between these two, right? So that's actually 180 degrees, not 20 degrees, okay? Because again, motion's going this way, force of friction is going that way. The angle between the motion and the force of friction, which is causing some sort of work on the object, it's displacing at some distance, is 180 degrees between the two, right? And so when you plug all that in, you get work is equal to a negative 3.012 joules. Negative because, again, the force of friction is going opposite of motion, and that means that the work being done in that direction would have to be negative. It's going against the other force. Okay. So we're going to stop here for today. We've gone over work for constant forces. So in the next video, we'll go over work with variable forces. So check out, like, subscribe, and comment any questions you might have. I'll see you in the next video. Thank you. Bye.